In this lesson, we're going to introduce a fair number of definitions and ideas. The particular definitions we work with, some will be useful, some will be less useful for us, but they're important for us to discuss. So we're going to take some time to talk about independent and dependent systems, and we're going to talk about the definition of the rank of a matrix, some connections between rank and the number of solutions we can get from our system, and also introduce the idea of homogeneous systems. So let's dive in here. And our first definition is about independent and dependent variables. In this case, if an augmented matrix is put into reduced echelon form, then every variable corresponding to a leading 1 in the matrix is referred to as a dependent or fixed variable, and non-leading 1 variables are independent or free. We actually saw this in the previous lesson when we solved out some of our examples. We ended up with a free variable, and we noted that because there was no leading 1 in those situations, that's how we identified which variable was free. So in this example, you can see we've got leading 1s for the first and second column, but we do not have a leading 1 in the third column because that row at the bottom has all zeros in it. So that would indicate to us that x3 is an independent variable or free. Just some different terminology there that we're adding in. So for our definition of rank, if an augmented matrix, again, is put into reduced echelon form, then the number of non-zero rows is called the rank of the matrix, and it's denoted by a lowercase r. And we get a few results out of this. There's 4 things we're going to talk about really briefly here, and I'll just make a few notes about some of these things. So first one here we have is that the rank of the matrix cannot exceed the number of columns in the augmented matrix. That is, that the rank cannot be bigger than or equal to n plus 1, where n is the number of unknowns in the system. And what this tells us in more practical terms is that when we reduce a given matrix to echelon form, if the number of rows exceeds the number of columns, we will have some rows of all zeros at the bottom. That's about the best we can get from that. Our second result says that if the rank is equal to the number of columns, then the reduced matrix will have no solution. So this particular statement is not all that useful for us at this time, since we would not necessarily know the rank until we've reduced the matrix anyway, at which time we could easily determine that there's no solution. Our third result says for a system of equations to be consistent, the rank must be less than or equal to the number of unknowns. Again, this statement is not immediately useful since we don't know the rank until the matrix has been reduced. And lastly, if an augmented matrix is put into reduced echelon form and is consistent with rank r and n unknowns, the number of independent or free variables is equal to n minus r. So this gives us the ability to predict the number of free variables once the matrix has been reduced. As with other situations, we would not know this until we've already started solving the system and putting it into reduced echelon form. So we wouldn't necessarily use this directly because we would be reducing the matrix anyway, at which point it would be obvious which variables are free and not. So here's just a few examples. You see in the first one, you've got 3 non-zero rows, so the rank is 3. And we also have 3 unknowns, and representing the number of unknowns in this situation, and we get a singular solution. In the second example, you can see we have 1 row of all zeros at the bottom, so the rank is 2. We have 3 unknowns, and we have 1 free variable then. And it's pretty clear again from that example that x3 is the free variable. And we have in the third example a system that has 4 equations and 3 unknowns. And in that instance, you can see that there are 4 non-zero rows, so the rank is 4, and n equals 3, the number of unknowns is 3. Therefore, we get no solution in that particular case. Again, we would have to reduce the matrix to know this information, at which point it's pretty clear that we have a contradiction on that last row, and we would then conclude that there's no solution anyway. So let's talk about this homogeneous system of equations. Essentially, the homogeneous equations are those that are equal to 0 for each of the, in this case, 3 equations. Some things to know about homogeneous systems: they always have the solution 0, 0, 0, 0, however many variables you have, which is referred to as the trivial solution. And generally, we don't spend a whole lot of time searching for that because, well, it's trivial. We know it's there. The solution to a homogeneous system is either singular, which would be the trivial solution, or infinitely many, which would involve a variety of free variables. So here's some examples that we can look at to illustrate the different outcomes. In the case of 1 and 2, we end up with singular solutions for both of those. And in the case of examples 3 and 4, you can see how we end up with infinitely many solutions in those cases. And these have just been put in row ref by me. So the last page on this one is just the possible solutions chart. I think this is kind of helpful. We'll add to this chart as we go through the quarter, but I think it's kind of useful to be able to kind of compare and contrast what we have for homogeneous and non-homogeneous systems and the kinds of results we could expect based on how many knowns and unknowns we have.